Alrighty, today we're going to carry on with our discussion on minerals. We're going to talk about mineral groups. Our objectives for this lesson are to classify minerals based on their mineral groups, of which there are 6, and also to relate mineral composition and self-arrangement, which we talked about in the last video lecture, to physical characteristics of a mineral. There are over 3,800 minerals that have already been discovered and named. Recently this year, in April 2015, scientists in Australia found a new mineral and named it putnasine. It was unique to any other mineral that had been ever formed or discovered before. All of our minerals on Earth can be classified into 6 groups based on their composition. Composition meaning what they're made out of here on this periodic table, so the elements that compose them. Our first mineral group is our silicates group. Silicates are formed with silicon and oxygen. Silicon is on our periodic table number 14 right here. So all of our silicates have this Si number 14 in it with a combination of oxygens, which is number 8. When these two bond together, they're either going to share electrons or they're going to become positively and negatively attracted to each other. We can also have SiO2 up here. When silicon and oxygen come together, they form a silicon-oxygen tetrahedron. All that means is that tetra meaning 3, so it's going to have 3 sides, and they create these triangles that kind of fit together like a tessellation. So they bond, go upside down, and fit together into this beautiful pattern. How those things bond is going to affect the structure, the external properties of the mineral. There's a couple of different ones that are listed right here: olivine, augitite, hornblende, mica, and quartz. These up here are our quartz. You guys have probably seen these before on the playground or outside while hiking. Our quartz is a relatively hard mineral. And then over here we have mica, which is also a silicate, so these are made out of the same base elements. And mica, you may have also seen that it's like flaky, relatively soft, kind of shiny. So both of these come from the same family. When we get our micas, these tetrahedrons are just going to form thin sheets, versus our quartz, where they kind of stack up on top of each other and have a more dynamic structure. Olivine here is in the middle of those two. So this is our picture of what olivine looks like. It also has magnesium in it. And this is our silicon-oxygen tetrahedra, and it's in the middle of mica and quartz. So if it was quartz, we'd see far more of these tetrahedrons stacked closer to each other, so that we're getting a really firm structure, whereas our mica will have just like a single sheet, one-dimensional. Silicates form when magma cools. Most of magma is made up of this element right here, silicon. So when it cools and crystallizes underground, we lead way to our silicate minerals. They can also break down, like quartz can break down and turn into a clay, which will also give us silicates. Our second mineral group is carbonates. Carbonates always have this CO3, which is 1 carbon and 3 oxygen. No matter what, if it has CO3, it's going to be a carbonate. This is our second most common mineral group. We see carbonates right here in this limestone structure in China. They're also in marble, which makes up headstones. In class, we're going to be looking at calcite. What's unique about this carbonates group is that when you place acid on them, they bubble. This is our 3D structure of carbonates, so we have the carbon and 3 oxygens. In China, you can kind of see this guy is getting worn away. Over time, he's getting more and more worn away. Pollution in the air creates acid rain. And although the acid rain is not strong enough to like sizzle your skin off, this acid rain does cause deterioration over time of this giant statue. It also happens with marble gravestones. Over time, the writing becomes worn away, likely due to acid rain. Oh, here's our marble, very hard structure. These form kind of in a cube-like structure, and we've got our carbon and our oxygen our calcium all bonded together here. Our next mineral group is oxides. Third one, they will contain oxygen and one or more other element, which is usually a metal. So we've got rutile, corundum, and hematite, which are all some examples. Our metals are going to be this light blue section right here, going over to this stair step. So the light blue and the pumpkin orange, pumpkin spice are our metals. So when we're talking about these oxides, we're going to have one of these things in here plus some oxygen. If you know anything about metals, when they're exposed to oxygen, they tend to rust. Our rust is going to be like a reddish, sometimes greenish, dark brown color. Most of these oxides are going to be that color. So here's some of our oxides. Scientists, whenever they sent up the robot to Mars, found oxide metals on Mars, which is what led them to believe that there was water there, because the oxides turned this rusty red color, and so they're thinking that there had to have been water to cause the metals to rust. Our next mineral group of 201 is sulfates and sulfides. Sulfates contain sulfur, and what distinguishes them from sulfides is that they happen when mineral-rich water evaporates. So we have a solution of water that has minerals in it, and when that water evaporates, it leaves behind the mineral crystals, and that's how our sulfates happen. They contain sulfur. Our sulfides will also contain sulfur. I'll show you where that is in a second on the periodic table. Gypsum is one that we have in class that we'll be looking at. Gypsum, we've got the sulfur, the 4 oxygens, and calcium bonding in there. And then our sulfides, how they differ from sulfates is that they form from thermal solutions. So if you've ever been to Mount Princeton Hot Springs in Colorado, it smells kind of like rotten eggs, which is a dead giveaway for our sulfur. Sulfates or sulfides, they'll smell like rotten eggs often. And when that mineral-rich spring water bubbles up, we're going to get an accumulation of these elements together, and it will give us our sulfides. Chalcopyrite and galena are examples of sulfides. They too will smell like rotten eggs whenever you place acid on them in the classroom, or sometimes in nature they just smell like that. They also have this cube-like structure, so no more tetrahedrons. On the periodic table, sulfur is right here, number 16. So if you see this S, singular S alone, you know it has to be a sulfate or a sulfide. Our next 5th mineral group is halides. Halides contain a halogen ion plus one or more other elements. What a halogen ion is going to be anything in row 7 right here. So fluorine, chlorine, bromine, iodine, adenosine, and then unknown, so not that one. So any one of these things are going to be in it, plus some other element. So from group 7A, halite, NaCl, is the exact same thing as salt. We have some halite in class that you can actually lick, and it will taste salty. I do not recommend licking rocks to see if they are halite. That's disgusting. Fluorite also is going to be a halide. It's made of calcium and 2 fluorines, which is right here. So we had NaCl, fluorite with an F. These ones are some of my favorite. They look like these big, beautiful cubic crystals, and they're like a tealy or a purple color. Sometimes they're also a clear color. And then our last group, group number 6, we're almost done, is native elements. They contain only one element or type of atom. These are going to be things that you probably are familiar with: gold, silver, copper, sulfur, carbon, all by themselves. Carbon can actually make 2 different elements. It can make graphite over here, which is what they put in pencil lead. So it scratches really easy. It comes right off the rock and onto your paper, so paper can scratch graphite, not very hard. And then we also have, from carbon, a diamond. Diamonds are the hardest mineral. So one atom can make 2 completely different things depending on how it bonds. In our structure of a diamond, we have multiple bonding, and it's creating this 3D interlocked structure, whereas in graphite, it forms singular sheets where we have weak bonding covalent bonding, forming in sheets. So the same element, carbon, can form two very different things depending on how its atoms self-arrange. In class, we will be growing crystals. This is going to be a class lab. We will do this lab in class. The objective of your assignment is to grow the largest crystal possible. We'll talk more about this in class. You guys are going to have to create your own procedure and materials list, do some research. Everything that you are going to need needs to be turned into me by Wednesday the 23rd, which is next Wednesday. You can use Google Docs to share your research and information. We'll talk about how to do that, and you have to create groups of no more than 3. You may work alone also if you want, or in a pair. We'll work in class to grow these crystals. We'll take measurements over time. The group with the largest crystal wins.